I'll try to talk today about graphene, but not only. I'll try to expand it a little bit more towards what we're doing now. So a bit will be on other materials, and you will see that we're challenging now much more interesting task than graphene itself. The easiest way to introduce this material is really to think about various forms of carbon in terms of dimensionality. Let me try to go forward on this, if it works. I hope it will. And just a couple of slides on trying to, for those who haven't ever heard about this material before. So if you think about various forms of carbon in terms of dimensionality, then of course the most well-known form is the three-dimensional form, the graphite, and we know it for a good 500 years. We will come back to this date later on. And about 20, 30 years ago, quasi-zero-dimensional form, its cage molecules or fullerenes have been discovered, and then a few years afterwards, quasi-one-dimensional form, carbon nanotubes, has been obtained. Now, it's quite easy to spot that there is a gap here at dimensionality 2, which has been filled in quite readily by theories. They introduced this fictitious material called graphene, but it hasn't been observed experimentally until recently. And if I ask you which of those materials has been researched theoretically the most, graphite, which we know for good 500 years, those two which we know for 20, 30 years, or graphene, which has been observed experimentally only recently, well, it's the graphene which is researched theoretically much better, of course, because it's the simplest possible form of carbon, so theorists don't really like complicated problems, so we know quite a lot about, we gathered quite a lot information by theory about this material, and it also used to predict the properties of the other three, because cage molecules, buckyballs, it's simply wrapped, graphene and carbon nanotubes is the road, graphene and graphite are the graphene sheets which are stacked one upon each other. Anyway, soon after its experimental observation, a lot of labs and companies around the globe jumped into this topic, and the reason why they are so interested is really the unique properties of this material. It's the thinnest possible material, the most conductive, the most thermally conductive, the most transparent, the most impermeable, and so on and so on and so on. And I always say that the most important in this list are those 3 points, because we come across new interesting properties of graphene basically every week. So there is of course no chance I can cover all of those topics in one talk. So I'll concentrate on the most important one, probably the fact that this is the first two-dimensional crystal, one atomic thick crystal, which is available to us. So you probably noticed that I stole the title of my talk from Edwin Abbott, his book Flatland, and this book, if you know it, it has 2 parts, and so as my talk. In the first part, as in the book, it will be placed in the flatland, in the two-dimensional world, and I'll explain why the fact that this is the first two-dimensional atomic crystal, why is it so important, and then in the second part we will go back to the space lab. So why this two-dimensional story is important. Let me give you two examples from the real life about this. So the first example takes us back to the 2 years back. I'm not sure if I'll find much support for this in this audience, but let's try. When Gunners were entertaining United at the Emirates Stadium, the sweet thing about this match is not only that United won quite convincingly, but it was, if you remember, it was the first ever football match which was translated in 3D. So in 6 pubs across England and Scotland, you can watch this game with just wearing goggles in 3 dimensions. And after that, both the Six Nations and the World Cup were shown in few cinemas in 3D. So it was extremely popular. And I always tell to my German colleagues that if it would be shown in 3D, if the World Cup would be shown in 3D in Germany as well, then all goals would be counted, not only the German ones. And then, so the outcome could be different as well. The second example happened approximately at the same time as the event of showing the football in 3D, is the release of the Avatar movie. I should admit, up to now, although I showed this slide already several times, I still haven't seen the movie by myself. But all my friends who have seen it, they divide into 2 groups. So those who did bother to go to cinema, they say that it's the best movie ever. Those who've seen it on the DVD at home, they say that it's complete rubbish. So it tells you that probably it's not the movie itself, but it's this impression of the 3D which makes this great impression. So, and that's why this title there, 3D is so real. That's what is really catching our imagination. So those 2 examples tell us that we generally hate this 2-dimensional projection on the wall. It feels absolutely unnatural for us. And it feels unnatural because our world is 3-dimensional. And our world is 3-dimensional, there is really a good reason for it, because low-dimensional objects, like 2-dimensional objects, they're not stable. If you here, what I show you here is the movie of 400 carbon atoms just thrown into a box and allowed to play by themselves. And sometimes you can see that they might form something flat, but at high temperature, if you allow significant time for them to evolve, they would eventually form something which is 3-dimensional. They would never stay. They would never form just flat objects. There are many reasons for that, of course, like termination of the dangling bonds, the surface tension, and so on. But the most fundamental one is probably the so-called Mermin Wagner theorem, the logarithmic divergences of the thermal fluctuations. At any temperature, if you have infinitely large crystal, those thermal fluctuations would basically kill the order in this crystal. So that's why everything around us is 3-dimensional. So our world is 3-dimensional, and that's probably the largest 2-dimensional object which has been available to us prior to graphene. Still, of course, it would be nice to have something from the other worlds, from the other dimensions, like the 2-dimensional objects. So how can we do it? Well, what I'm saying that our world is 3-dimensional. It's because it's really the temperature, the motion, the thermal motion of the atoms, which is killing this order. So and forbidden to growth, and generally all the growth is done at high temperature. So as you grow those materials, you simultaneously killing them at the same time. So, but then you can probably try to play a trick. You can grow something at high temperature and then cool everything down and slice it into individual layers, and in principle it doesn't contradict to anything. And that's not a very new concept at all. We're doing this with graphite, for instance, all the time. When you use pencil on a piece of paper, or you exfoliate graphite. So because it is a layered material, it's very easy to to exfoliate, you cut thin pieces of graphite. Those are left on the paper, and you see the pencil trace. The only question is, can we really exfoliate it so only one layer of atoms would be left? Well, quite a few groups, quite a few researchers tried that. What you see here is a pencil trace just done on a special substrate. That purple substrate is silicon oxide, and different thicknesses of graphitic pieces can be seen here as different colors. The whitish are the thickest one, and then the more bluish it goes, the more purple it goes, the thinner it becomes. And if you try hard, you can probably get into really single layer, and that's exactly what we've done some time ago. Of course, it took quite a bit of time to observe it for the first time. Our first samples were extremely small, but then with time our scribbles become better and better and better, and nowadays millimeter-sized crystals are not a problem at all. So we can produce this material. And once we produce it, we really came across a number of unique and very interesting properties. And most of those properties are down to this hexagonal structure, the hexagonal crystal structure which carbon atoms form in graphene. It looks extremely simple, but it's not the it cannot be categorized as the simple crystal structure. It's not one of the Bravia lattices. It has 2 atoms per unit cell. You can see I colored them differently, the green atoms and the red atoms. Of course, they are of the same color in the real lattice, but you still can distinguish them. Say all the green atoms would have a neighbor from the top or the red from the bottom. But then the fact that we have 2 atoms per unit cell gives us the wonderful electronic properties, and those electronic properties can be summarized by this graph as the linear dispersion relation for electrons. I don't want to bother you with all the physics. Let me just show you in one cartoon what are the consequences of this, believe me, unusual dispersion relation. So all the metals or semiconductors around us can be divided into 2 parts. It's either electrons which conduct electricity there, or holes, either negatively charged particles or positively charged particles which are conducting electrons there. To make connection to the real world, consider countries with single-party system like Russia or North Korea, for instance. You can move inside there quite freely. So electrons either in those semiconductors can move inside the semiconductor without any problem. But once you try to make a connection between those two, there is a great resistance at the border. To cross this border, you really have to overcome a lot of resistance, and that's exactly how our transistors work. You connect semiconductor with the p-type, where holes carry electric charge, and the n-type, where electrons carry electric charge. You connect those together, you create so-called p-n junction. So that's a diode. In graphene, the situation is very different because we have this symmetry. So we have both electrons and holes there, and this symmetry really guarantees us that we have that this resistance at the border won't exist. Those particles can be converted one into another very easily. In this sense, it is more like the United States with dual-party system. You can have one state being conservative, another one democratic, another Republican, but then you still can cross this border without any problem. Nobody would stop it. So that's exactly what happens in graphene. Those electrons can propagate through the wall crystal without any problems, extremely fast, not experiencing any scattering, and that's the property which we really like to use. Just to be complete, there is also, and in this sense, they really those electrons, they resemble neutrino, the massless particles. So you can also create other types of particles which don't have even analogy in relativistic physics, but I don't have an example of a country to illustrate those, so I won't talk about that. So the consequence of this extremely fast propagation of those electrons is that if you make a transistor out of this material, and it's quite easy to make a transistor out of this material, it would work extremely fast and at very high frequencies. The figure of merit there is called the mobility, is how much scattering your electron experience as it moves. The typical mobility which we can achieve in this material is quarter of a million. Of course, it doesn't tell you much until we compare it to something. This figure for a typical silicon transistor in most of the integrated circuits in the microprocessors would be 1,000, and in the best transistors which are in your mobile phones would be 50,000. So we are orders of magnitude better than the best transistors which are available to us at the moment. There is a problem, however, there which is also associated with this fundamental property of electrons, that they behave as massless relativistic particles, but I'll come back to this a little bit later. Also, the optical properties are governed by the same dispersion relation, and you can ask what kind of optical properties can you get from this. It's just one atom thick material. Can you see it at all? Well, apparently, quite surprisingly, you can, and when I said that it's the most transparent material, I was, well, not exactly honest with you, because it absorbs quite a large fraction of light, in fact, and it's quite surprising by itself. We have millions of atoms between me and you, millions of atoms of air, and I can see you easily. We have here only one atom of graphene, and it absorbs quite a large fraction of light. It absorbs about 2.3%. What you see here is a special sample. We have an aperture in a metal scaffolding. We have absolutely nothing here, free space. There is graphene, there is bilayer graphene, and you can see a contrast here, and this contrast is about 2.3%. So one layer of atoms absorbs 2.3%. That's already quite surprising. Even more surprising that this number, 2.3%, is not just a number. It's actually the combination of the fundamental constant. It's exactly pi times alpha. Alpha is the fine structure constant, 1/137. Do it at home, 3.14, divide by 137, you get 2.3%. So it's quite an interesting observation. You take a piece of graphene, you look through it, and what you see is the most fundamental constant of this universe, and that's quite exciting by itself. So, as I said, it's a large number for a physicist, but if you are an electronic engineer, you would kill to have a material which is as conductive as graphene and absorbs only a small fraction of light. It would be the central material for say touchscreens, for liquid crystal displays, for solar cells, and here we created a liquid crystal cell with graphene replacing the traditionally used indium tin oxide, and it works nicely. You pinch off the optical transmittance completely, and here we also benefit not only from high transparency and high conductivity, but also from the fact that it's an inert material, so it doesn't poison your liquid crystal, which is the most common problem for liquid crystal displays. So it tells us that applications are quite realistic, And I don't want to give you all the nice pictures of the future applications. Let me, in this part, let me tell you about the applications which are already there, which already had happened. And I hope that you would believe that also the future of this material is quite bright as well. So what graphene has done for us already? Well, it created workplaces, not many, namely 3. We had our former students and students of our competitors in US. They created several spin-off companies, not very large, but in this hard economic turmoils, every single workplace counted, so it's quite good. It also provides entertainment. If you watch the Big Bang Theory, then you might remember that in one of the episodes, so this sitcom, it's an American sitcom about a few Caltech postdocs, and in one of the episodes, this guy Sheldon, he's the string theorist in Caltech. He was trying to resolve the graphene problem, why electrons in graphene behaves as massless relativistic particles, and he was trying to solve this problem for the whole episode long, and it's not surprising at all because some of the formulas there are wrong. So, they're basically not for graphene; they're for bilayer graphene. So it also provides, gives shelter if you fancy and to go to live in US, in Tallahassee, Florida. You can quite as well live on Graphene Lane. Well, houses are not very good there, but it's a new street, so hopefully it will be better. But to be realistic, let me give you one example of the existing application. So graphene is extremely mechanically strong material. It's extremely thin and it is conductive. So you can imagine it's an ideal support for any object to be observed in transmission electron microscope, especially for biological objects. So here, that's exactly what we did in this experiment. You take graphene, freestanding graphene, you dip it into some solution of your biomolecules. You dry it. In this case, we used tobacco mosaic virus, and then you can observe them quite easily in your TM. No staining, nothing is required. I know nothing about TM or about biology, and it worked. It worked the first time immediately, and several companies now do sell it as a product. Transistor applications are a little bit more complicated, but we're still pushing for this, and it's hard to explain where this enthusiasm is coming from. Let me try to explain it in the historical perspective. You probably know that the first transistor, 1947, wasn't silicon; it was germanium. And it's only a few years afterwards that people realized that it is silicon which makes this wonderful interface with its own oxide. So they moved from germanium exactly one row up in the periodic table, and nowadays all the integrated circuits are based on silicon. Now we hear more and more about the Moore's law and which material is coming after silicon. Without even pretending that I know the answer, why not learn from history and again go up in one row in the periodic table, we arrive at carbon. So as I said, the mobilities are extremely good. It means that you can get really fast transistors. The problem is that those quasi-relativistic particles, they always travel with their own speed of light, and they cannot be stopped. The very reason which gives you this very good conductivity, it also tells you that it cannot be stopped. If it cannot be stopped, that it means that current cannot be completely quenched, and every single transistor needs to have two states. The on state, when the current flows freely through the transistor, and the off state when no current goes. And graphene has the problem with the second one, so you cannot stop the current through it. It would always go. It always conducts. It's not a problem for the high frequency transistors, and many companies, including IBM, they are trying to, they are researching on it, and they are trying to get into the terahertz regime with those transistors. But it's a problem for integrated circuits applications. But in principle, there are few ideas like making extremely small transistors, just few atoms across, and in that case, we can make it operating exactly as we want. Well, just let me comment on this, and it's a general problem. One of the problems which we are facing is not only to find the replacement for silicon, but it's how can we make transistors which are increasingly smaller and smaller and smaller. We are now on 16 nanometer technology. How can we make something which is much smaller than 16 nanometers? Generally, all the modern technique can be referred as paper cutting method. You take graphene, you carve away unwanted parts, and you form, I don't know, nanoribbon or transistor out of it. Same with silicon, you etch away unwanted parts. And that's exactly what is the problem, how to etch it away so precisely that you get the very high resolution there and the exact properties which you want. Well, graphene offers another possibility. You can, instead of paper cutting, you can probably do paper painting. You can, because it can be seen as a giant two-dimensional organic molecule. You can spray some. You can run some chemistry which can be self-organizing, and hopefully it can lead to self-organizing transistors. This work is being done now, and there are indeed indications that by self-organization you can get some interesting nanostructures in this material. So just to say that a lot of major applications are possible. Well, as I said, touchscreens, photo detectors, solar cells, tactile display. This is run by our collaborators, Andrea Ferrari and Nokia in Cambridge, and I really like this one. It's the tactile display. It would solve the problem of this type of phones with the touch screen. The beauty of the old phones with the buttons that you could use them at the lectures like this. Now you have to sit down and look into my eyes. And with the old phones, what you could do, you could secretly type the message, because you could feel the buttons. With the phones like this, you simply cannot feel the buttons. You would have to look into it, and I would see that you're not listening. So, but with the tactile display, you could feel the buttons on the flat display, and it would solve the problem of a boring lecture like this. So, well, RF transistors, gas sensors, strain gauges, variable capacitors. So there are really a lot of possible applications which we can do with graphene. But for some time there was quite a problem, a challenge. Is okay, we can do it, but where can we get this material? This LCD display which I showed you was 30 micron. Of course, for your lounge, you want not 30 micron, you want 30-inch display. And where can we get graphene, which is 30-inch wide? And let me again put this a little bit into perspective and tell you about the mass production of graphite first. I'm not sure if it is relevant to the lecture, but just I enjoy it a little bit by myself. So graphite, you might know that graphite was first found in Borrowdale Valley, close to Keswick, not that far from Manchester, and you still can go there. Nice, some of those tunnels are hand carved, and you can still pick up some graphite there. And the first mentioning of graphite in the royal papers is 1564, and already 1565 we see the mentioning of graphite in the book of Konrad Gessner, published in Zurich in the year of his death. And if you think that it took our collaborators from Zurich to come over to Manchester and learn the exfoliation technique, it took them about 3 years to bother to come, and it took about just 1 year from here to here. Well, Europe was quite united that time, and it's probably less united nowadays. But English were extremely fast in realizing the strategic importance of this material, and they limited the production in order to inflate the prices. Those mines were opened only once every 7 years, and that indeed did the trick. The prices for graphite at that time were extremely high. It was about £1 per pound, and £1 sterling at that time was the weekly wages for any worker working in the mine. And you can imagine it would immediately promote a problem of stealing of graphite. You could just go there into the mine, slip this piece of rock into a pocket, and here you are. You've got your monthly wage in your pocket, literally. So the problem was so severe that they had to push for a special legislation through the parliament, asking for, and they treated illegal access to mines and illegal trade of graphite as a very serious felony, for which the punishment was the public whipping and 1 year of hard labor. So I always tell to my students that this law is still in place in our lab at least, and if you touch graphene once, you're condemned for 3 years of hard labor as PhD, and then public whipping at your viva. Well, the very name of this slide, the black market, they say that it originated from the illegal market of graphite, which existed in 17th, 18th century Britain, and this is not my idea, it's from the Pencil Museum in Kassel. Nowadays there is a reasonably legal gray market of graphene. I showed you there are few companies on the market, one of them opened by our former students, and they trade graphene at some ridiculous price, £1 per square micron. They just came with it out of nothing. And initially it was just enough, barely enough to cover their postage expenses because the samples were extremely small. But then as we progress, as technology progress, nowadays we quite easily create millimeter-sized crystals. So if you extrapolate the price, you would pay 1 million per single sample, which is of course ridiculous amount. I always tell them that it's very unsustainable business, but they're still there. They still exist. I don't know how they do it. Luckily, there are now a few other methods how to produce graphene, and we can indeed produce really 30-inch pieces of graphene, which are enough for any applications, and you can indeed use it for realistic applications. And there is so-called CVD method. There is epitaxial growth on silicon carbide. For composite materials, you can use liquid phase exfoliation. So this problem is more or less solved now. So we have quite large. We can get large quantities of graphene quite cheaply nowadays. So let me just move a little bit away from graphene. One of the reasons why this whole research was so popular now, so many labs across the world are doing this, is because the entry cost is so low. You basically buy high quality graphite, £100, buy silicon oxide substrate, £20, you buy piece of scotch tape, £1, so for £121 you are in business. Now, if you want to splash a little bit and buy not only one pencil, but the whole set of colors, you can a little bit, well, you have to spend some money sometimes, but you can expand your research into other materials as well. And we tried those other pencils as well, and you can exfoliate other materials. You can create monolayers of other crystals like boron nitride, some dihexagonides, some complex oxides like bisco or IPCA or molybdenum disulfide, boron nitride, as I said. So all those crystals, they do exist. Some of them, or the vast majority of them, are stable in the two-dimensional form, and their property in the two-dimensional form is very different from the property of the three-dimensional precursor as well. You can also, there is another way how to make new two-dimensional crystals. You can consider graphene as a molecular scaffolding, as an organic molecule, and so which you can run chemical reaction on, and you can attach something to those carbon atoms. For example, you can attach fluorine. You get fluorographene or two-dimensional Teflon if you want, or you can attach hydrogen. And you get so-called graphene, and those two are very different materials from graphene. Their properties are different, their crystallographic structure is slightly different as well. So really the importance of graphene is not in its own properties, but in the fact that it opened this floodgate to other 2D crystals to be created and started. So we have graphene, which we researched for a few years now, but then we also started to work with other two-dimensional crystals, and there are even more two-dimensional crystals which are available to us, but which hasn't been researched practically at all. So let me now switch to the very short, I won't bother you for much longer, very short second part of my talk. So the first part was in the two-dimensional world, in the Flatland. Let me now go back to the Spaceland, according to Abbott, into the three-dimensional world. And how we do it, so I said that we can exfoliate many different crystals. We can exfoliate graphite, boron nitride, molybdenum selenide, molybdenum sulfide, and so on and so on. But now, if we have those individual two-dimensional crystals, why not try to put them together in some random order? So we would basically, we can take graphene, we can take molybdenum sulfide, we can take another layer of graphene on top, so we can create new stacks of those materials in any fashion we want, and we would get into a completely new material which doesn't exist naturally, but we can tune the properties of this material and we can make it functional as well. We can make, say, those layers to behave as transistor, those as photovoltaic device, another one is the solar cell, and so on. So you bring the functionality of your devices on the material level. I should probably warn theorists in the audience, you don't need to write down the exact composition of this guy. It doesn't exist yet. But we started to work on this and say those things, they do exist already, and probably our record now is about 20 layers of different two-dimensional crystals stuck on top of each other. And believe me, it's quite a painful job to do. So we don't just stack them mindlessly. We have some idea how it should work, so that each of those 20 layers, it has its purpose, and it becomes multifunctional material or multifunctional device. So I said it's quite a painful process to go through. At the moment, we're doing it really by hands. Just take one layer of one material, another layer of another material, put them together, take another one, put them on top. But basically, because we can tune we can take any material we want, we can tune the property of the resulting heterostructure, of the resulting stack, according to our wish, and we call it layer by layer material engineering. So even the simplest stacks like this, we take boron nitride, graphene, boron nitride, they already show very interesting results. For example, the quality of graphene stack between two boron nitride level becomes extremely high. Well, just a good example is the observation of the fractional quantum Hall effect in such stacks. Don't be much bothered about this, but so it just tells you that we really get new physics and the very good quality of those. And then if we have two layers between of graphene stuck between boron nitride, which is an insulator, you can study transport not only in plane but also out of plane between tunneling, for example, between those two layers, and surprisingly, even single layer of boron nitride acts as a good insulator. It shows some exponential behavior, and you take a few layers there, it becomes the behavior becomes different, and it is even more. Well, it's clear exponential behavior for say 4-6 layers of boron nitride. We also made a transistor out of it. You put graphene, molybdenum, boron nitride, molybdenum sulfide, graphene, and then you can gate it, and you can tune the current through this stack, and it acts as a transistor which actually works, and it can be used in the integrated circuits. And because it is vertical, we don't have a problem with sizes. We can make it as small as we want. And then the type of physics which we find in those materials is extremely exciting, because we can really make very complicated structures now. So, and that's exactly where we and many other labs are going into now. And it's this new, just to conclude this part, the Spaceland and the whole talk, to say that graphene is an interesting material, but the real importance is that we have now this new class of materials, the two-dimensional atomic crystals, which allows us this new type of research, the layer-by-layer material engineering, or materials on demand. And I will stop here. Although I would also like to thank my collaborators, first of all, Andrew Geim, of course, quite a few academics and postdocs and PhD students in Manchester, and it was really a good and pleasant community to work in with our collaborators both in Europe and in US and in Asia. Thank you so much.